So thank you for tuning into this video, and in this particular one, we're going to just talk about the biosecurity risk mapping workflow that's available on EcoCommons. So we'll just get tucked in by going into the platform and having a look at what you can do. So if we log on to EcoCommons and we go to the analysis hub, and the modeling wizards, there's something called the risk mapping modeling wizard that you can click into. When you do that, you see this sort of what is the bare bones of what you're going to create. And basically, you're just going to work through this tree in order to, at the end of you're building this model, you're going to come up with a pest establishment likelihood. So the pest establishment likelihood is simply 3 probabilities multiplied together. So it's your abiotic suitability times your biotic suitability. So your abiotic suitability is, are the conditions in your area of interest in Australia, are they suitable for your pest to survive, reproduce, all the rest of it, right? So are the climatic, is it too cold for them? Is it too hot for them? Too dry for them, right? So that's your abiotic suitability. And then that's multiplied by your biotic suitability, which is essentially, is there sufficient host material in that part of Australia for your species to survive? I mean, maybe your species requires fresh water. Maybe your species requires trees, right? Maybe your species requires cattle. So maybe you have a layer that highlights cattle density throughout Australia. That's your biotic suitability. Where are your host biotic components for your pest? So if your pest were to arrive, where are the biotic things that it relies on? So abiotic suitability times biotic suitability gives us pest suitability. And our third thing that we're multiplying together is our pest arrivals probability. So the pest arrivals probability is, well, how many of these pests do we expect every year to get through the border crossing and into Australia? So even though we have biosecurity border checks, every now and then we're going to get things that get through those checks. How many things are going to get through those checks? And then of the things that do get through those checks, how many of them are going to be viable when they arrive? When you open up your container or your mail or whatever it is, how likely it is that that pest is actually going to be in a state where it can thrive and reproduce and grow. So pest establishment likelihood, it's just these 3 probabilities multiplied together. Abiotic suitability times biotic suitability times your pest arrival probability. And one of the first steps that you can take is define your study region. So in this case, we've defined that, and this is the default, is, well, we're interested in creating a risk map for the whole of Australia at 1 kilometer resolution. So the little grid cells that make up this map are 1 kilometer by 1 kilometer. And we're going to work in a GDA 94 Albers projection. And basically what that means is, if you're not familiar with geographic projections, you've taken a round version of the, the sphere that is the Earth, and you're portraying that on a map. When you do that in a projected coordinate system, a couple of things happen. One, you get more accurate spatial relationships and area if you use the right projection. And 2, when you use a projected coordinate system, you're usually projecting from decimal degrees or degrees latitude and longitude into meters north-south and meters east-west. So in this case, the default map, the coordinate system is in meters and it's projected in this CRS. And you can learn more about the CRS by clicking here, right? So that's the first step. You could have chosen Queensland as your study area, or you could have chosen an LGA, whatever it might be. So then what other steps do we need to take before we really get stuck in? And I would argue strongly that, so on one level, it's really simple to create a risk map. It's just abiotic suitability times biotic suitability times your pest arrivals probability. But each one of those things, you can come up with each one of those values in a variety of different ways. Highly encourage you to do some background reading if you're not already an expert, to seek out some experts, maybe to hold a workshop, those kinds of things. But we do have support articles. So if you go to support.ecocommons.org.au, you can find information about how to do different parts of this workflow. We also have a support article that's not quite live on the website, but it should be in the next day or two, which walks through how to run a biosecurity risk mapping workflow, right? So there's all kinds of things that you can do. So this explains the workflow. I think we give some examples of what it kind of looks like. So there's a bunch of support material that you can look at. But importantly, that support article, or this support article, links to things like this report by James Carmack. So James is a researcher at the Center for Excellence in Biosecurity Risk Analysis, CEBRA. They're based at Melbourne. All of the biosecurity algorithms and workflows that we have are put together by some very clever people working at the University of Melbourne at this CEBRA facility. And they have great reports on, and this is an example of one of those, and they have papers. So I would really, and especially this report for this workflow, I'd really encourage you to check it out, get familiar with some of that information. So if you're not familiar with risk mapping, I'd encourage you to study up on it because there's a lot you can do in that space. If you're not an expert already on the species that you've been tasked with creating a risk map for, so for the pest species that you're worried about. So in this case, we're worried about mouse ear hawkweed. So if you're not familiar, it's this cute little weed. It looks almost like a dandelion, but it just takes over alpine areas, high altitude areas. It's done that a lot in New Zealand. It's actually already arrived here in Australia, but is being controlled. But that's an example of a pest that you can do a risk assessment on, or generate a establishment likelihood map. And there's a lot of information about the mouse ear hawkweed, right? One of the sources for that information is something called CABI. They do all kinds of other things, but they also have information on a variety of species. So this is, covers off, some of the different names, what it looks like, the taxonomy. So to look for different taxonomic names when you're pulling together your occurrence data. Gives you a description of what it looks like. Talks about the distribution. So where is it found? Where is it native? Where is it introduced? Talks about how it's been spreading around the world, the risk of introduction. Importantly, it's identifying, hey, you know what? This is the main way that it's spreading, and that it's arriving in other countries. So a lot of people are ordering these pretty little seeds online or whatever it might be. So that's one of your major pathways, right? So all kinds of good information. This is just one example of where you can get that kind of information. The Australian government has a lot of it. CEBRA has a lot of it. There's literature on these things. So there's a lot you can learn about the biology and ecology of mouse ear hawkweed. And importantly, you can read about, when it's likely to spread. So when does it reproduce? but importantly, the physiology of your pest can be a really nice constraint to understand. So if mouse ear hawkweed does not survive when it is over 35 degrees for more than a week, right? And you know it also doesn't survive if you don't get X amount of rainfall per year. If you know those things, conservatively, you could build an abiotic suitability layer by just putting an environmental envelope that excluded all the areas in Australia that are below that minimum amount of rainfall and get too hot, right? We would argue that you might want to create a species distribution model because we know there's a variety of conditions that the mouse-eared hawkweed might survive in, but there's some of those conditions where they might actually thrive. And a species distribution model will give you an understanding of the probability of how well the hawkweed will do. But anyway, that's lots and lots of information. So do your homework on your species, obviously. The other thing, if you're developing a distribution model, for example, for mouse-eared hawkweed, it's worth highlighting that often you're going to be developing a model that is inclusive of the species native range. So for mouse-eared hawkweed occurs primarily in Europe. So we might want to build a species distribution model based on just the records where it's native and it thrives. And then predict, based on that model that we've developed, where would it have suitable climatic conditions in Australia. So we might want to generate a species distribution model. If we did that, we would be using global data from GBIF. The best way to get that data is to go to the GBIF website, go to occurrences, type in the scientific name, say I only want preserved, so we've got 700,000 records here, but say I only want preserved specimens because I'm certain that each one of those preserved specimens that's in a museum has accurate lat long and accurate identification of the mouse-eared hawkweed. So you might only want to use those records. You might only want to use recent records, right? So if we use all of the records, you know, we're going to get a bigger data set. But if we only want to use recent records, you know, we're going to get a smaller data set, right? So you can filter these things. And maybe we only want the European data. Again, if you're generating a species distribution model, there's two schools of thought. You can build a species distribution model using the species native range. So in that case, we select Europe. Or you can use a species distribution, generate a species distribution model using all of the occurrence records throughout the world, right? And that way you're capturing all of the variety of environmental conditions that it's known to occur at. Two schools of thought. A lot of people tend to build one from the native range and then predict into the novel environment, but other people will prefer to use all the available data. What's great is you can do that in a few minutes in GBIF, right? And then when you download this data from GBIF, it'll mint a DOI for you, which means you can send that DOI to a collaborator and they can click on that URL and it will open up the same data set that you've filtered out. What's nice is GBIF is also developing the capacity to, let's say you and your collaborators are working on this data set and you find some errors and you correct those errors. You can actually mint a DOI for that curated data. So a lot of cool things happening in the data space. But this is where you would get your occurrence data generally for most risk mapping data sets. We do have an API connection with GBIF, but it doesn't currently allow you to do a lot of this filtering or to mint the DOI. So I just recommend you use the website for now. So we've got some occurrence data that we've identified. We know a bit about our species. We know a bit about the workflow. We've done our homework. Now we're ready to do a risk map. And I just want to flag before we get started that Biosecurity Commons. So we've borrowed this workflow from the Biosecurity Commons folks who have the risk mapping workflow there available as well as a bunch of other workflows, the species distribution modeling they're using from us, but then they're building things like dispersal modeling, proof of freedom, surveillance design, all these other workflows that are coming and will be launched in May of next year. So if you're interested in biosecurity, Biosecurity Commons is a great place to go. Check it out. However, here today we're talking about EcoCommons, right? And the risk mapping workflow that's available here. So if we go into, so this is our base of our tree, right? But we're going to flip over into here where I've already filled this tree out. So it took me probably 2-3 hours to do all this. And some of it was because I was looking up, oh, what parameters do I need to put in here and that kind of thing. So it didn't take too long, but it took a little while. So we'll just go through a completed workflow. So at the top of the tree is pest suitability. We're multiplying, to get that, we're multiplying abiotic suitability and biotic suitability. If we go to abiotic suitability, in this case, we're choosing to use a species distribution model, right? We've developed that in EcoCommons in a separate workflow. So in fact, we've taken 7 species distribution models and we've averaged them in a process called an ensemble modeling process to get this map of where we think the mouse-eared hawkweed will find suitable conditions in Australia. So it's in these areas where there's high elevations, and we'll probably do pretty well in Tassie, probably do pretty well, and we know it's already pretty well established in New Zealand, right? So it's created a pretty good result. We'll walk through that in separate videos. We're not going to go through the species distribution modeling stuff here. But what we can do in this risk mapping workflow is we can click on add a new input, and we can select from our results that mouse-eared hawkweed ensemble model, and we're using the average result. So we've selected that, and that's the only one we have available currently, but I could select different kinds of inputs. So I could upload an input. Maybe I've created a layer that is a nice environmental envelope of the physiological tolerances of my pest species, and I'm just going to upload that data. Or, you know, maybe I want to draw in some of the curated data as, you know, I'm going to draw in a temperature map or something, or explore my data sets or choose from my results. So we click on choose my results to find that species distribution model that we've already run. So we'll cancel that for now. And if we go up there, you'll notice that when we click on abiotic suitability, so you would have seen that ensemble model included predictions for Indonesia and New Zealand. That's not our study area. Remember, we set our study region to 1 kilometer resolution map of Australia, and that's what we get, right, in our results. And so that's our result for abiotic suitability. The map looks a little different just because the scaling is visualizing a little differently than it was in our ensemble, but it's the same data that's producing this map. Okay, so that's abiotic suitability. We have a whole nother couple of videos on how you create SDMs that you can put in abiotic suitability. For biotic suitability, there's a whole lot of options that you could use to select a biotic suitability layer. So you might have a density map of cows in Australia, and you know you're dealing with a cow-borne pest, or a pest that's reliant on cows to survive and reproduce. So you might just have a map here of the density of cows, right? In our case, we've got mouse-eared hawkweed. So what we're going to do, and we'll go to this other work, we'll go to this example just to see the initial steps. So we're going to take something called the National Vegetation Information System. So if you're not familiar with it, it's just a map of vegetation classes around Australia, right? So there's all these different vegetation classes. And what we're going to do is we're going to say, well, we know that mouse-eared hawkweed might occur in tussock grassland, hummock grassland, maybe other grasslands. It's probably not going to be in chenopod stuff. It's definitely not going to be in mangroves. We're going to select the places where we're definitely sure that it could occur and exclude from this tick list the places where we're sure that it won't occur. So we're sure it won't occur in the mangroves. We're sure it's not going to include, be growing in these naturally bare areas, right? Whatever it might be. And then what's going to happen is you're going to generate this map, this map where all the things that you've ticked are identified as being suitable areas where this thing could grow, and all the areas that were left unticked are unsuitable. So when we go to view that result, this is the result. Now I probably ticked a few places I shouldn't have, right? I think I might have ticked a chenopod shrub kind of habitat or something, because the ones is all the places where I'm saying there's biotic conditions that are suitable for a mouse-ear hawkweed to grow. Probably a lot of this country is not suitable, so I might have clicked something inadvertently. But you've masked out effectively all these zero areas. In your final pest establishment likelihood, when we use biotic suitability in this way, you're masking out all these areas that are red. So these red areas will not be in my final map, because my probability that I'm multiplying here is 0 and 1. It doesn't have to be 0 and 1. So I could build a species distribution map for cattle in Australia, right? If I didn't have a density map of cattle, maybe I'm going to build an SDM for cattle, and I could use that probability of occurrence as my biotic suitability layer. Or maybe I just want to stack a bunch of different components of biotic suitability. Maybe land use is important, so I want to classify a land use mask. And then I combine those biotic suitability layers by combining those different layers. In this case, we're just using NVIS. But you get the idea that, yes, it's simple. You're just going to generate this probability, but there's a lot of different ways you can do that. Okay, so the final of the 3 probabilities that you need to generate is something called a pest arrival probability. And we might click on this one. No, we'll click on this one first, but we'll go here to just show you what that looks like when I'm starting the workflow. So if I click on pest arrivals, I can add a new input. So I might have some inside knowledge on how pests are going to arrive, how many and how viable they're going to be. And so I might generate a generic pathway for my specific pest. But there's some established pest pathways that already exist. So I might pick, for example, the tourist pathway. So you remember that tourists might be bringing mouse-eared hawkweed back in their luggage from traveling somewhere where it's pretty in Europe. And if we build that, so we add that pathway, we're going to get some different components of that pathway. So there's a component called the accommodation distribution. So that's where are all the good hotels that people are most likely to be spending their time in. And then there's this layer that's called airport distance weight. So what's happening here in the airport distance weight function is you're taking these little airport locations, and you could upload your own airport locations if you want to include Alice. I don't think it's included in this particular one. And then you need to do some math. So we're going to define this parameter called beta. So beta, what beta is defining is an exponential decay function. So it's shaped, kind of like that. The default, I think, is, well, there isn't a default. Oh, well, it suggests a default of a log of 0.5. So that's a moderate curve, right? So, And what's that suggesting is when I fly to Melbourne, I'm most likely to stay in the Melbourne area. And maybe a little bit further out from Melbourne, but as soon as I start to go way out from Melbourne, right, my probability of going that far as a tourist is much lower. Most tourists are going to stay pretty close to town, right? So you're defining that function, and the 200, so that's how many kilometers, what's the furthest distance somebody is going to come into Melbourne might go before that curve flattens out to 0. Right? So it might be 500 kilometers, it might be 200, whatever it is. And you actually have to do the math to, take the log of 0.5 and divide it by 200, and you get negative 0.3 or whatever it is. Right? And you enter that value. When you do that, and we go back into our tourist pathway, we get this map. So I'm most likely to go to Perth and stay in Perth if I'm carrying a hawkweed. But there's a small, tiny little chance that I might go way out here to whoop whoop, right, and drop off a hawkweed seed. Then another pathway that you would have noticed in the CABI website was seeds arriving in mail, right? So I've gone online, I've said, oh, hawkweeds are sure cute. I'm going to order one and have it delivered to me. Well, where are those hawkweed seeds going to arrive? Well, they're most likely to arrive in the places where people live, right? So all we're using here to define our pathway is the density of people, right? So this is where people live, so this is where most likely those seeds are going to arrive. And then, so there's an important step within each pathway that you define. So you could define 20 pathways if you wanted to, 20 different ways things might come into the country. But part of that defining those things is if we go into the input parameters, there's 2 parameters that we have to define before we calculate this mail pathway. And the first one is the leakage rate. So in this case, they're parcels of mail. So we have biosecurity controls at the border that catch things before they get into the country, right? How many packages each year do we think are going to come into Australia and get to that person with mouse ear hawkweed inside of them, right? How many of those packages are going to arrive? Or if it's a container pathway, how many containers are going to arrive? How many ships are going to arrive? If it's a ship pathway, right? And we're suggesting, well, we're not really sure. But if we put a distribution around that, and we'll say the lower bound of our 95% distribution is, well, at least one's probably going to come in every year. And at most 10 are going to come in every year, right? So we're defining our distribution. So that's our leakage rate. And then our viability rate is, okay, I've ordered this thing in the mail. How likely is it that I'm going to be able to plant it in the ground and it will grow? How likely is it that it will be viable once it comes in through the mail, right? Well, if it comes in the mail, it's going to be, there's a pretty high chance that it's going to be viable. We're saying 30% is the lower confidence interval and 90% is the upper confidence interval, right? So we're fairly sure that we're going to get a few packages with mouse-eared hawkweed coming into the country, right? With viable seeds. When we click run for this run mail pathway, it's going to say, okay, these are the parameters. This is the likelihood of it arriving at any one place. And this is sort of the map of where it's going to arrive. And it gives us a probability. And then the final step is calculating the pest arrival probability, which is just simply the statistical union of however many pathways you have here together. So you'll notice if we look at the log scale, because these values are quite small, you'll notice the map is combining that tourist pathway and that mail pathway, depending on how you parameterized the likelihood of that pathway existing. you'll remember that we said it's more likely that viable seeds are going to be arriving through the mail, right? So you're seeing that have a bigger impact than the tourist on your map, and that's a statistical union allows you to do that. Okay, so we've got our pest arrivals, we've got our biotic suitability, we've got our abiotic suitability. We multiplied abiotic and biotic to get our pest suitability, which sometimes you want to use separately. That's why that's done. And our final step, we're going to calculate our pest establishment likelihood. The probability of it arriving at any individual location is fairly low. And it's relative to the way we parameterize this workflow, right? So we couldn't compare, I got 0.3 probability for mouse-eared hawkweed, but 0.5 for hoof and mouth disease. You couldn't compare those two things because you would have used totally different ways of getting to that final result. But the map still is giving you the relative probability. Where are these risks? Where are the places that are most risky for hawkweed to be arriving and establishing themselves? Given the abiotic suitability, the biotic suitability, and where they might arrive. And that map looks pretty good, actually, for mouse-eared hawkweed. That's actually where a lot of them are unfortunately found. They might extend a little bit further north here, but so this is just a demonstration case. I would encourage you, if you have any questions, you want to get in touch with us, just visit ecocommons.org.au. We've got a little contact spot that you can get in touch with us, all kinds of other information. You can sign up for our newsletter. And if while you're running one of these things, something doesn't work or something doesn't make sense, please click on the feedback tab on the right, add your feedback and add your email address and hit submit. And we'll be able to improve the services that we're providing. So thank you for tuning into this video, and feel free to tune into I might see you in the future video. We'll see. Thanks.